Today in this presentation, we're going to talk about a cooperative game and application. Group members are Ruyi Zhang and Daocheng Yang. In a strategic environment, non-cooperative games focus on a player's own decision-making and is irrelevant to other players. The game does not only contain conflicts. Often, in many cases, it also contains cooperation. Cooperative game is fundamentally different from the types of games we have studied so far. Cooperative game consider the set of joint actions that any group of players can take. The outcome of a cooperative game will be specified by which group of players forms and the joint action that the group takes. The key difference between cooperative and non-cooperative games is that in cooperative game theory, players can make the binding agreements before playing the game, for example, how to share the payoffs. But in non-cooperative game theory, on the other hand, agreements are not binding. Non-cooperative analysis is biased toward individual, local, and anonymous behaviors, and therefore a short-run time frame. Whereas cooperative analysis is biased toward societal behavior that provides a long-run view. But we should note that in both cases, players are self-interested. Cooperation does not imply selflessness. In daily life and socio-economic activities, due to the limit of power or the lack of financial resources, a person or group seeks cooperation from others to form a coalition in order to overcome their own weakness. Once the alliance is formed, players must act as a whole with the goal of making the best interests. Once the game ends, the players will share the outcomes according to the distribution of the contribution. Cooperative games are often defined in terms of a characteristic function which specifies the outcomes that each coalition can achieve for itself. For some games, outcomes are specified in terms of the total amount of dollars or utility that a coalition can divide. These are games with transferable utility. But for other games, utility is non-transferable, so we cannot characterize what a coalition can achieve with a single number. For example, if a coalition of consumers can reallocate their endowment between themselves, then the utility possibility frontier in general is not linear.
Hello, this is Daocheng Yang. Here I will introduce the Shapley value and the core in a correlation game. First, let's make an assumption of transferable utility. It means that the payoffs may be redistributed among a correlation's member. For example, if the payoff is money, it is possible to divide that money among a correlation's members. Under this assumption, let's look at the definition of correlation with transferable utility. A correlation game with transferable utility consists of two parts. N is the number of players, which is, we assume here N is a finite of players, which is indexed by I. V is kind of like the utility function in the correlation game. For any subset S belongs to N, the payoffs that a correlation S can get is Vs. Here we assume that V empty equals to 0. Now let's look at the definition of superadditive game. We say that a correlation game is superadditive if for all subset S and T belongs to N, if the intersection between these two subsets are empty. So let's make a new correlation, S union T, that combines these two correlations together. So the value of this new correlation is that is at least as big as the sum of the value of the two correlations independently. In other words, it means that the value of two correlations will be no less than their individual values. So, if the game is super additive game, we can easily draw the conclusion that the best correlation will be the grand correlation, which means everyone participates in this correlation. As long as we know that the best correlation is a grand correlation, which means that every agent participates in the same correlation. So how are we going to distribute payoffs among the agents? Actually, we can do it either by considering the fairness or considering the stability. Now let's look at the Shapley value. The Shapley value is a way of distributing payoffs considering the fairness. The Shapley value is actually characterized by a collection of desirable properties, such as symmetry, dummy players, and additivity. So the definition of symmetry, dummy players, and additivity are shown in the slide. Here I want to focus on the definition of interchangeable. So interchangeable means that if there are two players, I and J, if they contribute the same thing to every possible correlation, it means they are interchangeable. So what is dummy players? Dummy player means that this player contributes nothing to the correlation. It means that the correlation with him or without him, the payoff will be the same. So actually, the Shapley value is the unique payoff division that divides the full payoff of grand correlation and that satisfies the symmetry, dummy players, and additivity. The mathematical expression of the Shapley value is shown in the slide. So here, phi I is the payoff that the player I can get from the correlation. As we can see, S is the number of players in the correlation, and N is the total number of players. So the last part is the marginal contribution of agent I. It means that the payoff of the correlation with player I minus the payoff of the correlation without the player I. The Shapley value can also be expressed as the two following expressions. To conclude, the Shapley value is actually captures the marginal contribution of agent I, averaging over all the different sequences according to which the grand correlation could be built up. So next I will show you an example to help you better understand the Shapley value. Here is the example of the Shapley value. Let's suppose that Alice, Bob, and Selena want to share a meal together. Here is the case. If Alice eats alone, it will cost her $80. If the case that Bob eats alone, it will cost him $56. If Selena eats alone, it will cost her $70. But if Alice and Bob eat together, it will cost them $80. If Alice and Selena eat together, it will cost them $85. If Bob and Selena eat together, it will cost them $72. If they want to eat together, it will cost them $90. Now let's compute the Shapley value for each player in this case. I will just explain the first three cases because of time limitation. So now let's look at the first case. In this case, Alice comes to the meal first. Bob comes to the meal after Alice. Selena comes to the meal after Bob. As we all know, it will cost Alice $80 for this meal if she eats alone. Now Bob comes. It will cost them $80 for this meal. That means Bob has to pay $80 minus $80, which is equal to 0 for this meal. Similarly, Selena comes to this meal. It will cost her $10 for this meal. Now let's look at the second case. Alice comes to the mill first. Selena comes to the mill after Alice. Bob comes after Selena. It will cost Alice $80 if she eats alone. Selena comes after Alice. It will cost them $85 if they eat together. That means Selena has to pay $5 for this meal. Bob comes after Selena. So in this case, it will cost them $90 for this meal. So that means Bob has to pay 90 minus 85 for this meal equals to $5 for this meal. Now let's look at the third case. Bob comes to the meal first. Alice comes to the meal after Bob. Selena comes after Alice. It will cost Bob $56 for this meal if he eats alone. Now Alice comes after Bob. It will cost them $80 for this meal. So that means Alice has to pay $24 for this meal. Now Selena comes to this meal. It will cost them $90 if they eat together. That means Selena has to pay $10 for this meal. Similarly, we can compute the other three cases in this table. So after the computation, the Shapley value in this game is that Alice pays $39.2 for this meal, Bob pays $20.7 for this meal, and Selena pays $30.2 for this meal. After discussing the Shapley value, let's move on to another way of distributing payoffs in a correlation game, which is a core. The core is another way of distributing payoffs in correlation games, which based on the stable ability. Now let's look at the definition of the core. A payoff vector X is in the core of a correlation game if and only if the sum of payoffs to the agent in any subcorrelation S is at least as much as they could earn on their own. Knowing the definition of the core, now let's look at the existence and the uniqueness of the core. Here I want to introduce two definitions and one theory. Now let's look at the first definition, the simple game. A game is a simple game if for all subset S in the N, the payoff can only be either 1 or 0. For example, if there are 100 persons voting to pass a law, only in the case which more than 51 persons vote yes, this law is passed. So in this case, there are only two different payoffs. The law is passed or the law is not passed. So obviously, this game is a simple game. So the second definition is the vital player. So a player is a vital player if the payoff without him will always be 0. Now let's look at the theorem. In a simple game, the core is empty if and only if there is no vital player. If there are vital players, the core consists of all payoff vectors in which the no vital players get 0. Now let's look at the definition of a convex game. As we can see in the slide, the condition is more strict than the superadditive game. Here there are two theorems. The first theorem is that every convex game has a no empty core. The second theorem is that in every convex game, the Shapley value is a core.
Then we will move to a real-life application. In southern China, Jiangsu province is building a number of power plants. The central department chooses three transport companies to undertake the equipment transportation tasks. Three companies have their own transfer stations and transport network, can be within the specified time to deliver the material to the destination. So the problem is, how should the three companies' transport tasks be allocated to meet the lowest transport cost and make reasonable use of the various resources to ensure that the three companies are most cooperative? This case is not only about to deal with the optimization of transportation cost and time. It's more about considering the issue of project management and coordination of interests. Therefore, we can study from the perspective of cooperative game to solve the problem of transport distribution. As we can see, here is the transport network diagram. There are two blue dots, which are the starting point and the terminal point. And we also have three gray dots, A, B, and C, which are the transfer stations of three companies. The yellow arrows stand for the transportation routes, and the numbers on the arrows mean the maximum transport capacity on the route and its corresponding transport cost. And here we have some notation and formula. Now we go back to the transport network diagram. So without regard to transport cost, VS refers to maximum capacity of players. On the contrary, in consideration of transport cost, the maximum transport capacity can be weighted by using unit cost. As the transport capacity is a benefit type indicator, so the value is of course the higher the better, and the transportation cost is a cost type indicator. The value will be smaller the better, so the capacity can be divided by the unit the unit transport cost for a simple weighting. So at this point, Vs represents the maximum transport capacity weighted by the unit cost. So the optimal allocation strategy of the project is shown as below. When I equals 1, the subsets of S which contain player 1 are 1, 1, 2, 1, 3, and 1, 2, 3. Then we can calculate the phi 1 equals 15. Similarly, the phi 2 equals 46 over 3 and phi 3 equals 4. Then we verify the results. We can see that the phi 1 is greater than v1, phi 2 greater than v2, blah 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 blah, and all checked. And we can see that the solution is very stable. Shapley value represents the cost-weighted average traffic allocated by the transport network to which each player belongs. The amount of traffic between each player can also be calculated. X12 represents the weighted traffic between player 1 and player 2. X23 represents the weighted traffic between player 2 and player 3. So after the calculation, we can see that x12 equals 1 and x23 equals 1/3. So here we have the optimal allocation strategy as shown on the slide. So the results of the cooperative game transport allocation methods show the proportion of the final flow distribution, how three companies tackle the transport tasks according to their own transport capacity, costs, and resources. Cooperative game theory provides us a high-level approach. So when we are optimizing the transport cost, we should also consider the stable relationship, which is conducive to the long-term cooperation and development. And that's all of our presentation. Thank you.